Everybody hears me? That's okay? Okay, my pleasure to be here today. I'm Dr. Michaud from Université Montréal in Canada, and I'm working with the Eaglet since 2 years from now. We do some, obviously, fitting, and we do some research out of that machine, and we enjoyed to get that technology for our patients and for our students as well. So here are my disclosure. I'm fortunate to be paid by many major companies in contact lens field. So at the end, I'm not really biased because everybody pays me. So okay, next one. Okay, what this machine brings to our offices is the unique technology to be able to really measure accurately the topography of the conjunctiva. We know a lot about the cornea. We know how to measure it. We have a good topograph in place, and we know exactly how to deal with these curves and these very irregular surfaces sometimes that we have in cornea, and we know how to adapt our contact lenses based on the topography maps. But on the conjunctival side, we don't really know up to this point what was really the reality of that surface. And it could be really irregular as well. Okay, next one, please. We know that the conjunctiva will be irregular mainly because of the insertion of the right muscles. And these right muscles are not placed exactly on a symmetrical position. So this is why the conjunctiva is non-symmetrical toric surface. And the larger that you can fit a lens on that conjunctiva is 24 millimeter, because you have this insertion in the nasal size with the width of 5 millimeters and 7 millimeters in the temporal. So it gives you 12 millimeters in addition to the 12 millimeter of the cornea. So the larger that a scleral lens can be is 24. Believe me, I didn't fit those larger lenses. The maximum I fitted was 20 millimeter, but most of the time I prefer to rely smaller, because with smaller diameter lenses, we deal with less conjunctival toricity, so we have less adaptation or modifications to do and less troubleshooting to do at the end of the day. If you look based on the Yves van der Werp work at Pacific University, to my point, if you look at the 15 millimeter diameter, you will get 1.5 diopter of conjunctival toricity around, in average, around the cornea. But if you go to 18 millimeter, you will end up with 5 to 6 diopters of conjunctival toricity in average. So that means that if you go larger than 15 millimeter as a scleral lens, you will have 90% of the time to fit lenses with toric haptics or back toric surface to adapt in every of these meridians to get the lens to be well aligned on the conjunctiva. Otherwise, you'll get spherical haptics and you'll get a full alignment in one quadrant, but you'll get a misalignment, either a compression or an edge standoff in the other meridians, and that complicates the fit a lot. That complicates the fitting of the lenses. So, and it's variable from one patient to another patient, but more than that, it's really variable from one eye to the other eye. You cannot just take in account that you get a mirror situation between the two eyes. The two eyes are really two different worlds. So we need that kind of machinery to really evaluate and measure the conjunctival surface outside of the cornea to better design our scleral lenses and to get a better success at the end of the day. But again, if you keep your diameter of scleral lenses inside 15 millimeter, and this is very possible, then you can have spherical peripheries. But larger than that, 16, 16.5, 17, 18 millimeter scleral lenses, you will need 90% of the time to address the toricity of the conjunctiva to be successful in your scleral lens fit. Again, these are coming from University of Pacific University data. The variation between the superior, inferior temporal and nasal side, as for the transition between the cornea and the conjunctiva, is very minimal. But if you go larger than that, between 15 and 20 millimeter, the transition, the angles between the cornea and the conjunctiva varies a lot, and from quadrant to quadrant. Again, the rationale is that if you don't have the tools to evaluate those variations, it's quite impossible to guess how to design your scleral lenses. In some patients, the difference will be 100 microns. In some other patients, it will be 400 microns. So you never know, and there's a lot of trial and errors implicated if you don't rely on really accurate data. And as for transition, we have this picture in mind as the regular shape of a human eye. But since 1981, that study was made in Germany, and we know that most of our patients, in fact, are showing that profile, meaning that the transition between the cornea and the conjunctiva is mostly tangential. So that drives the way you will fit your scleral lenses and the way you will address your peripheries, and you will design your peripheries as well. Next one, please. If you don't get the Eaglet machine or other devices allowing to measure the conjunctival surface, the only way to address and to evaluate the sag evaluation, the sag height of an ocular surface, is to look on an eye from the side. Obviously, it's not really precise, and your judgment is as valuable as mine, but for a normal eye, we know that, for an average 16 millimeter lens, we have to rely on a 4.3 or 4,300 micron sag value. And if you have a keratoconus, we assume intuitively that it will be a little bit more higher than that, but it's not always the case. Because if you look at keratoconus, the keratoconus is mostly situated and located down and inferior to the cornea. That doesn't mean that it's the most elevated point in that cornea. This is not the apex of the cornea. If you have the Himalaya or volcano in Australia, that doesn't mean that at the equator side on the planet Earth, you're not more elevated. In fact, you're more elevated here. And the principle of scleral lenses is to vault over the entire surface. So really mapping the cornea and the conjunctiva will help you to determine where to look at and where are the highest points where your fitting begin to be crucial. OCTs obviously help you to evaluate the landing. The important point to consider is that if you work with larger lenses, 16 and over, you need to balance the weight and the support of that lens with higher clearance under the surface. That lens becomes very highly vaulted over the cornea. Then you land with more mechanical impact on the conjunctiva, and you disrupt more the mucin on the goblet cells and the lipids coming from their membranes as well. So larger lenses with higher vault will disrupt more the conjunctiva, and you'll get mucin and lipids. And because you have a high vault, you have also a high space over the limbus. So these debris will gather in the bowl and will accumulate over time. So you get fogging for most of the lenses that are not really well aligned. One of the ways to alleviate that to occur is to get a better alignment of the lens in every quadrant and to really customize the way the lens is landing. If you work with smaller lenses, or if you customize your peripheries, you bring the ceiling down and you'll be able to adapt your landing to reduce the mechanical insult on the goblet cells. So you reduce the mucins that is liberated, and you reduce the lipid coming from the cell disruption as well. So you get less debris, and you can also adjust the clearance over your limbus. If you limit the clearance to less than 100 microns, at that point there's no way the debris will come in play, and you'll in fact eliminate all the fogging that are associated with larger lenses. Again, so either you work with smaller lenses, which is my way I prefer to work with, or if I no choice to go with a larger lens, then you have to adapt that large lens quadrant by quadrant, but you have to work with the information in the data coming from those devices. Other ways to do it is to use an OCT, and it could be really complicated because the scan of an OCT is certainly not any larger compared to what the Eaglet gives you. You'll get 9 to 10 millimeters at the most. So you have to work with composite images, and you have to use the caliper at a given chord or a semichord to estimate each of these angles and estimate the sag value over the cornea, over the limbus, and over the transition zone. So it's really, really demanding and cumbersome at work. You can just have this measure here, and in a matter of few seconds, you have all the information that you need in order to design the perfect lens for your patients. Here are some applications, and this is an example of where this machine could be useful. This is the right eye of that patient and the left eye. Obviously, the keratoconus on the left eye is more advanced. If you look at the keratometry, it's around, we'll have that on the next slide. But just based on the color map of these two eyes, we know that the keratoconus is more advanced here. So, by intuitively, we would think that this eye gets a more elevated surface and gets a higher sag value for the ocular surface compared to that one. But look at the data and look at the reality. So the keratometry, the SIMK value is 77 by 87, and this one 48 by 51. But the overall sag of that eye is 404 at 15 and 392 at 15. So quite similar, despite the fact that we have a very high keratoconus, very elevated keratoconus based on keratometry. This is still a very limited surface over the entire cornea, located very down and low. So that means that if we measure with that machine the ocular surface, then we realize that the ocular surface are quite similar between the two eyes. So it will save me time, because I would have started my trials with very high sag value scleral lenses here. Obviously I would get too much volt and with no clue about how to reduce it. So many lenses. Based on those data, I know that I can take 4,000 microns lenses plus 300 microns of clearance to vault that ocular surface efficiently, and then the map tells me where exactly I'll have to look, because the red color are the highest point of that ocular surface. So I know in advance that where my clearance should be an issue is over the apex of the cone for sure, but also in this area here on the superior temporal area. This is another application of that type of data that we get from the Eaglet. You have a normal cornea here, but the blue color tells you that the conjunctiva of that patient is way lower as for the height of that surface compared to the rest of the ocular surface. And in those cases, it is not quite rare to have, can you advance please? Okay. Not quite rare to get conjunctival prolapse in such circumstances with larger lenses, because of the mechanical impact and because there's no tear exchange. In fact, there's diffusion toward the inside of the bowl. If you have a loose conjunctiva, kind of conjunctival chalasis. With a lower surface like this one, then just the suction effect from the dynamics of the fluid under the scleral brings that conjunctiva to drop over the cornea, and we call that conjunctival prolapse. It's considered a benign phenomenon with no long-term known effect. But as a practitioner, I'm not really comfortable with that kind of thing because I know that they are covering the stem cells over the limbus, and that can, impinge the oxygen delivery to the cornea. So when I see this type of mapping, I know in advance that I'll have to deal probably with that. So again, either I design my peripheries differently, and or smartly, I will just reduce the diameter of my scleral I will work with in order to get lower negative pressure or lower suction effect, and to limit the space here so the conjunctiva will not be brought over the cornea, and I will alleviate the conjunctival prolapse. Again, it's proactively telling me what kind of lens or what kind of modification I will have to do with my regular lenses, and that in fact saves me chair time. Post-graft patients, again, can be really challenging. These are probably the most fragile patients that we have to fit in scleral lenses, namely because the graft itself is always under a kind of a rejection scenario, but the endothelial cell count can be really reduced. And we know that with larger and thicker scleral lenses, we can really impact the oxygen delivery to the cornea. And it's not quite rare. I saw some cases where the graft become opaque in a matter of few days if the clearance is too high or the thickness of the lens is too high. So by doing a mapping of those surfaces, I also know where to look at in order to vault efficiently that surface. Certainly the junction, the graft to host junction is crucial, and that the graph tells me exactly where to look, again, at the apex, and here also at the graft host junction. Next one, please. It also tells me that this part of the cornea is way lower, so I'll get probably a higher clearance than expected here. As for regular fitting, we looked at one of the lenses I'm working a lot with is the Blanchard lenses, the one-fit lenses. These are truly scleral lenses, 14.9 millimeter. So we vault over the cornea, we vault over the limbus, but with a limited diameter, which is efficient for probably 85% of my patients. So we looked at how we can match what we found with the Eaglet and what we fitted as a base curve or sag value. These lenses are labeled in base curve even if they are designed with sag value in mind, but we find a perfect correlation. To this point, I'm really doing my mapping, and boom, it helps me to select my initial lens to try on that patient. In fact, I can even order empirically my lenses based on those findings. Next one, please. So in conclusion, that type of technology helps you certainly to customize the fitting of your scleral lenses, not only to know in advance what will be the outcome, but in fact, it will tell you exactly how to manage your peripheries and the design of your lenses, the diameter of your lenses, in order to be more effective. At the end, it saves chair time, it's more efficient, it eases the fitting process, and it's one of the only instruments that can evaluate the profile and the sagittal value of the ocular surface up to a chord of 18 millimeters. So it's really, really efficient, and it changed the way we fitted our scleral lenses. So I would be around to answer to any question. I thank Eaglet for inviting me to share my experience with that machine, and I thank you very much for your attention.